We're recording now. Okay. Trying to see on my computer if I'm okay. Yes. Um, this is the last unit that we're doing this semester. It has to do with thermodynamics, and we're just going to touch the surface of it this semester. Next semester, next time when you take Gen Chem 2, thermodynamics will become essentially one unit of the course. It's a very, very important part of Gen Chem 2. But I need to lay some foundations here so that you'll be prepared to do that in Gen Chem 2. So the first thing we want to look at is force and work. Work is the energy that is expended when an object is moved against a restraining force. Now, it's written as W, work, is minus F times dl. Now, what this is, and I got this negative sign in red to highlight that, because you're thinking about, say, if I'm thinking about positive work, I'm putting work into a system. Remember, anything going into the system is positive, anything coming out of the system is negative. So if I'm doing positive work on an object, I need to move it in a direction that I'm calling positive, and my plus direction. If the force that is resisting that is what determines the work I do. If there were no force of resistance, there would be no work done. So the force that is in this equation is not the force you apply. It's the force of resistance of the object you're trying to move. Take, for example, gravity or friction on the plane. If I'm sliding something on a plane, the someone's mic is open. Okay. If I'm sliding something on a plane, it's the force of friction on that plane that would go here. So I'm applying a force. If I'm applying my force in the positive direction, the force that's causing the work is in the reverse direction. So it'll be a negative number. And so I'll have a negative number for F. I need a negative sign out front so that I get positive work done when I move the object in the positive direction. Okay, let's look at the little cartoon. Here's a little guy on a big box. He can apply much force as this green arrow, but the friction against the plane is this blue arrow. It's much larger. So he can push as hard as he wants and he will do no work. Now, look, a key feature of work is something has to move. A boundary has to move if work is done. If the boundary doesn't move, no work is done. No matter how much force you apply, you have to actually move a boundary before work gets done. Now here's the same guy, but now he's got a smaller box he's pushing. And he can still apply this green amount of force, but the box is only going to resist by this much. So there is a net difference in the force. Newton's second law says that an object, when you apply a net force to it, it will accelerate in the direction of the net force. And that means its speed gets, it not only moves in the direction that you're moving it, but it will get faster and faster and faster. It accelerates in proportion to the net difference in force. So this guy would be running down the block like that because he's able to move the object from here where it started to this now where it ended. So delta L isn't zero, and he did do some work. So again, the takeaway from this little cartoon is work requires a boundary to move. If the boundary doesn't move, like in the first case, no work is done. If the boundary moves, that the boundaries of that little cube move from its starting point here to its ending point here. And so work was done. And notice the amount of work was proportional to this blue force, the resisting force. It's the force of opposition. Very often textbooks say that, but then they never write it out. It's just work is minus F delta L. And it makes the assumption that the force is the same as the force you apply. Now, in Gen Chem 2, we'll address this issue again. And in the limiting case, for the maximum amount of work, you would need to apply a force equal to the resisting force. Now, you know, if you did that, it wouldn't move, would it? So what they will tell you is that you're going to apply just an infinitesimal amount of force greater than the resisting force, and the object would move, but it would take forever to get from place to place. So this is what we call a reversible process, where the force you apply and the force of resistance are set equal to each other. And so the object doesn't move. But if you gradually increase your force just a tad, a little bit, then you will move the object a little bit. And if you did that in the limit, that would give you what's called a reversible process. And then the force applying and the force opposing would be the same, but it would take an infinite amount of time to actually do that process. So this reversible process isn't possible in reality, but you can approximate it, and it turns out that when we do some calculations later on, we can calculate what it would be if we could do it reversibly. Okay, so a system is going to possess energy if it can do work or if it can transfer heat. Now, I didn't say if it does work or transfers heat. I didn't say that. I said it possesses energy if it can do work and if it can transfer heat. Either one of those would tell you that the system is possessing some kind of internal energy. Now, we see energy in lots of different forms, but kinetic energy is one we've talked about before, and that's what we would talk about in the case of the little guy pushing the block. He would be moving that object, and it would have energy that would be of this form called kinetic energy. And the equation for calculating kinetic energy flow is 1/2 mass times velocity squared. So the speed of an object is really, really important in determining what its kinetic energy is. That's why if you have an accident and you're traveling at a high speed, you're much more likely to get killed than if you were traveling at a low speed when the same accident occurred.
Hey, Dr. Pearson.
Yes.
I am so sorry to interrupt right now. And I'm sorry to interrupt the class. This whole morning, my Wi-Fi and everything has been down. So I just got on and I missed the quiz and I missed everything.
Okay.
I haven't missed a quiz. I haven't missed anything in like this whole class. And I was really hoping if you could give me a chance to make that up because my Wi-Fi company completely shut everything down.
Okay. Contact me by email after the class, and I can open it up for you to take it later.
Thank you so much for that.
I know things like that happen, but it's a real tricky issue I'd like to discuss with you personally too.
Okay.
All right, so kinetic energy is 1/2 mv squared. Now let's think about the units for energy is joule. That's the SI unit for energy is the joule. The mass is kilograms, and velocity has to be in meters per second. So if I look at the units for a joule, we can use this equation to define the units on joule. If this is joules on the left, and that's kilograms, and that's meters per second, then a joule is a kilogram meter squared per second squared. That would be the deconvolved units that make up a joule. And you can use this law to determine what the kinetic energy is and the units. Now, there's potential energy, and an object can possess potential energy because of its position or its composition. That is, if I have a rock on a hill, it's going to have more energy than it does if it's down in the valley. So since energy tends to flow outward of objects, remember, everything goes from where it is to where it isn't. So the energy would dissipate to the rest of the universe if that rock went from the top of the hill down to the valley. So the spontaneous direction is for the rock to fall down the hill. You're not going to ever see that rock all of a sudden roll up the hill by itself and then freeze solid or something. That's not going to happen. We'll have much to say about that in Gen Chem 2. It turns out those types of circumstances are not impossible. It's just they're so highly improbable that, again, I'm not going to tell anybody if I see it happen. I'm just going to pretend I didn't see it. I'm going to rub my eyes and look somewhere else and think, no, that didn't happen. They come and get you with this big white coat with long sleeves, and they put you in it and tie them sleeves in the back and throw you in a rubber room if you see things like that. I don't want to do that. If I'm thinking about chemical potential energy, a balloon that contains methane and oxygen has more energy in it than it would have if it was converted to carbon dioxide and water. So if I fill a balloon with methane and oxygen and put it over a candle, it will explode and convert the methane and oxygen to the more stable carbon dioxide and water. And that energy then would be released in the form of the explosion that you would see happening. You can have energy because something's hot. Now, a hot object contains more energy in it than it does when it's cold. Now, here's the problem with heat as a form of energy. You cannot, if you've got a rock on that hill, you can tie a string on that rock and you can put it over a pulley, and then you can go down to the bottom of the hill and tie a smaller rock onto that, and then you can roll the big heavy one off the top of the hill and it'll lift the other one up. And all of the energy that's in that potential energy of that object can be used to lift something else, to do mechanical work. Now, the other forms of energy are not always totally transferable into useful work. The chemical reaction I told you about certainly is. You explode methane and you explode gasoline, your car would do methane too. But you explode a fuel inside the cylinder, and that chemical explosion that's taking place, the chemical reaction that's taking place, that conversion of energy because you had a fuel and oxygen to carbon dioxide and water, that energy can be used to move your car. Turns out that is a thermal process, and it really can't all be used. Thermal energy is I usually tell people that heat is the place where good energy goes to die. I mean, it's going into something and it's going to warm it up. That object's heat energy is going to stay in there until you physically touch it with something colder. If you didn't physically touch it with something colder, it would stay hot forever. It wouldn't transfer its heat. It only transfers it to a colder object. Now, what's going to happen? The hot one's going to get cooler. The cold one's going to get warmer. When they come to the same temperature, no heat will, the heat will stop flowing between them. While that heat's flowing, though, I can put a machine in there, like a steam engine or something. I can take that heat energy and boil water and make steam. And I can take the pressure of the steam to move a piston. And then I can allow the steam to escape and the piston go back, and I can keep that going. But what's happening is this water, as it forms steam, it pushes the piston back, and then the steam, once it's exhausted, gets converted back to liquid water, and that process is continued. But whenever you have a heat engine that is between this hot object, the boiler, and the cold object, the air, that allows that heat to transfer. If you had everything up to the temperature, even the surroundings, if you had the steam in the boiler and the engine and the air around the engine all at the temperature of the boiler, the train wouldn't run. It wouldn't move, because you have to have a hot object in contact with a cold object. Once that happens, there is no force in the universe that can keep that heat from flowing. And so it can do some work, but it can't convert all of that energy to work. Why? Because it has to touch the cold object, and some of that energy is going to go to the cold object. In fact, in most cases, your car probably is operating about 7 or 8% efficient. Probably somewhere like 92 to 93% of the energy in the fuel you burn actually just goes to heat the air up. It's only a very small fraction of it that actually can be used. So thermal energy is a form of energy, but frankly, it's not a very good one. And when you talk about solar energy, yes, we've looked earlier when we talked about the greenhouse effect and everything. The amount of solar energy that the Earth receives is far more than the whole world would use in a year. We're getting that much probably in a few days. But we can't use it very easily because it arrives to us at maybe 15 to 20 degrees Celsius. And you have to expend it then against something colder than that. Maybe you might have a solar collector that you can heat up to a couple of hundred degrees maybe, but the air is going to be like 25. And so there's going to be some transfer of that heat. In fact, the majority of it's going to be transferred as heat from the hot object to the cold object. You're going to get very little of it actually used to do mechanical work. So we've got plenty of solar energy, but it is a heat form of energy, and heat always involves losses. You'll hear people talk about waste heat, and as if it were something people were being wasteful about. But no, there is waste heat in any heat process, but it's not waste in the sense that you could recover it. You can't recover it. It's required to be wasted outside of the machine you're trying to operate because of the very nature of what heat energy is. So you've got to have a hot and a cold object to ever transfer thermal energy into any kind of work. And in Gen Chem 2, I'll tell you the very simple equation that you can use to predict what percentage that is. I'll tell you here. If you took the temperature of the hot object in Kelvin and the temperature of the cold object in kelvins, subtract the two, and then divide that by the temperature of the hot object, that's the percent of fraction multiplied by 100. That's the percent of that energy that gets transferred into work. T high minus T low divided by T high. Do the calculation if you want to. Your car's got probably about 180 degree Fahrenheit thermostat in it. So you can convert that to Celsius, and then you can convert that to kelvins. So that's going to be your high temperature for your car. And then the low temperature is the air temperature. Say you're driving at 80 degree outside temperature. Put those together and calculate the efficiency of your car. You'll find it's extremely low. Okay, so a temperature is a measure of amount of heat energy that something contains. But I've shown you this before, but I'll remind you. Here we've got, I think I showed this way up in the beginning of the course. If you have an object, a thermometer in a chamber that's at 25 degrees and 1 atmosphere pressure, maybe nitrogen gas, and you have a little tiny hole between the high pressure side and the vacuum, then obviously the gas is going to flow through the hole. At the temperature, right up close to the hole, we've measured temperatures as low as 2 degrees Kelvin. And when you measure far away from the hole, it's back to 25 like it was here. The explanation we showed you was the molecular motion. The only particles that got out through the hole were the ones that were headed toward the hole. So this someone's got your mic on again. So this opening allows the molecules that were traveling toward it to go out. So when they first come out, they're all uniform, moving in the same direction. They're not moving at the same speed. If they were moving in the same direction at the same speed, the temperature would actually be absolute zero instead of 2 degrees Kelvins. So these fast molecules hit the slower ones, and eventually they bounce off each other until they reproduce this pattern of random motion that was characteristic of this side. So the nature of temperature is that it is a measure of the randomness and the motion of molecules. The more random they are, the higher the temperature is. Now you do have to put heat energy in to do that, to cause that randomization to take place, or it will suck it from their surroundings, and that's why we got the 2 degrees down here. Okay, so this is another thing to remember. The temperature is a measure, and it is hotness. It's just exactly what you think of when you think of something being at high temperature. You think about it being hot. That's what it means. But it's a measure of the randomness of the motion at a molecular level. Okay, now, so you got a temperature for a collection of particles. You can't really have a temperature of one molecule. It's a temperature, you have to have enough molecules that you could not predict where the molecules would be at some future time. There's just too big a sample to ever do that calculation. Okay. Now, I've mentioned this to you before. The kinetic energy of any sample, solid, liquid, or gas, is just 3/2 R times T. Okay. Please keep your mics turned off while we're doing the lecture. Okay. The SI unit for energy is joules, and it's in kilograms per meter squared per second squared, like we talked about earlier. You do need to know that unit. Now, the first law of thermodynamics is the law of conservation of energy. It just says that the total energy of the universe is constant. And we can make use of that concept if we think about we've got some system that we're studying. And maybe it's a beaker in a lab and it's got some sulfuric acid and maybe some sodium hydroxide, and we're carrying out that neutralization reaction. But it's a piece of the universe we've isolated to study. The rest of the universe that we call the surroundings. So this defines the universe. The universe is a system we've isolated for study, and then everything else. And when we talk about it like that, we mean everything else. I always tell people we're including the third moon of Jupiter, okay? So if I'm putting energy from the surroundings into the system, I can put it in the form of heat. Now remember, heat going in makes the energy go up. It's a positive flow when heat's going in. The other way I can put energy in the system is in the form of work. I can do work on the system to make that happen. And if I put some heat in and do some work, I'll move the internal energy of the system up with both the heat and the work. And I'll go from this initial state before any went in to this final state when both went in. And that change in energy then is equal to the heat supplied plus the work done. This is a statement of the first law of thermodynamics. The change in internal energy is the heat supplied plus the work done. And we're only assuming those are the only two forms of energy we can put into the system, is heat and work. Now that'll be true if you're not dealing with charged particles, if you're not dealing with any kind of external fields that moving from one place to another would cause a change in energy. Our systems are there is a gravitational force, a gravitational field, but we don't have to take it into account because we're not really moving the beaker around in a gravitational field. So it has some forces of gravity that's acting on all the particles, but the beaker is sitting in the lab, not moving, and so it doesn't matter much. And whether a molecule is at the top of the beaker or at the bottom of the beaker doesn't change enough for us to ever even imagine measuring it in any way. So we leave out those fields. And we don't need to worry about electric and magnetic fields unless we've got charged particles, and then we would have the ability to put electrical energy by moving the charged particles around. So anything going into the system is positive. Now we're going to start looking at some what we call state functions. And simply stated, a state function is anything that you can do an initial state and a final state, and the change in that function, if it doesn't matter how you got from state 1 to state 2, that's a state function. Something that is independent of how you get from place to place. If I'm thinking about my coffee cup, which I am right now, it's sitting on my desk here. Now, it has a different amount of energy on the top of on my desktop than it would have if I set the cup on the floor. So the amount of energy difference is just determined by the gravitational field constant and the height of my desktop to the floor. That's all that matters about the internal energy in a gravitational field. So it doesn't matter whether I pick my cup up gently and set it down on the floor, I'll get that certain amount of energy. If I were to pick my cup up gently and hold it up in the air and then take it and set it down on the floor, the heat energy would still be the same. The gravitational energy difference would still be the same. It wouldn't matter. Now, if I could just knock it off my desk and let it hit the floor, now the energy would be the same, but my coffee wouldn't be. It'd be all over the floor down there. I'm not doing that. I used that as an excuse to get a drink of coffee. Okay, but you get the point. It's a state function, and internal energy is a state function. When we wrote the change in internal energy as Q plus W, it didn't matter how we did that. It didn't matter whether we did it fast or slow. It didn't matter whether we did things in between the two states. You just got through doing an experiment on Hess's law, and we made use of that concept. In one of the reactions, I can span a certain amount of chemical energy, and then I might do another reaction and take that reactant down to some other product, and I'd have two reactions taking place. The heat flow from the initial state to the final state would be, I could do that all in one step. And like you did, you turn reactions around and calculate heat for that big jump. Or I could do the first step, and then I could do the second step and add them together. See, internal energy is a state function, and that allows you to do that. That's why Hess's law works, is internal energy is independent of the number of steps you go through. We only need to know what the initial state is and what the final state is. Now, we're going to look at internal energy. Certainly, we've already defined that is a state function. We've used heat flow in reactions, and most of the time we called it heat flow, but if it takes place at constant pressure, that's a state function also we call enthalpy. So we've got those two functions that you're going to talk about in Gen Chem 1. In Gen Chem 2, we'll add two more functions. And if you stay with PChem, they'll add one more up there. All right, so now here's an illustration of what we're talking about. I've got my little green box or my coffee cup sitting on top of a little orange box of my desktop. And I imagine there is a ramp going from the top to the floor. And I can imagine pushing that object off the ramp. Now, the ramp has friction on it. And so as the box is lowered, the potential energy is going to go down because I'm going from this level to something smaller. So the gravitational potential energy would go down. It would be doing some work in that it would be doing work against this frictional force. So there would be some work done. And if I'm doing it at constant velocity, slowly, then the potential energy decrease would equal to the work that was done. So I could keep sliding that right off down, and I'd see the potential energy going down, the work going up. And when I got to the end, the potential energy would have dropped from this value to this value, and we might call that a zero. You can define your reference state or your zero state any way you want to, and a logical one might be to call the potential energy of the floor your zero, because you can't get below the floor easily. So most of the time you're going to stay in the room and nothing can't get lower than the floor. So we could call that a zero if we want to, that's okay. And then we see that amount of work done going off the ramp this way. So the potential energy got completely converted into work going by this pathway. Now, I can take the same pathway down, except go off the side of the box. If I go off the side, then there's no friction, no resisting force as it falls down to the ground. It would fall to the ground. Oh, might cry. I'm trying to be funny. Breaking up my little box when it hit the floor. But anyhow, the same amount of potential energy happened. It went from this state to this state. That was a state function. Look what happened to work, nothing. So work is not a state function. Potential energy is. So if we want to measure work, we have to do it along a path like this where we can calculate what it is. And in a case like this, there's no resisting force, and by definition, you can't do work unless you have a force of resistance. Okay, all right. So the state of a system is defined by a set of intensive variables. Intensive variables are those that do not depend on how much stuff you got. Like, for example, temperature. If I measure the temperature of a beaker of water, I can pour that beaker of water out into a smaller beaker, and measure the temperature and I'll get the same number. I can go pour some of it into a smaller beaker. I can still get the same number for the temperature. I could take one drop out. If I could get it on the thermometer just right, I could measure the temperature. It'd still be the same. So intensive variables are those things that we can measure for our system that don't depend on how much mass or how much of the system we have. It's an intensity. It's the same for the whole sample. If I'm talking about pressure in gases, it's like that. The pressure, it doesn't matter where you put the pressure gauge in your container, you're still going to read the same pressure. If you took that same amount of the gas and somehow or other you could just reach in and get a bottle of it and take it over here, take that little bottle and put your pressure gauge on there, it'd still read the same. So pressure is independent of the amount as well. So temperature and pressure are. Now, the number of moles is not. I mean, you know, if you got 2 grams or 4 grams, you got twice as many moles in the 4 grams as you had in the 2. So mass or number of moles is certainly not an intensive variable. It's what we call extensive. It depends on how much stuff you've got. Volume is the same way. If I measure the volume of 1 mole of gas or volume of 2 moles of gas, same temperature and pressure, the volume of 2 moles is going to be twice as much as the volume of 1. So those things are extensive variables. But if you did the ratio, the molar volume, the volume that 1 mole would occupy, then if you took the volume and divided by moles, the molar volume is an intensive variable. So gases, if you remember the ideal gas equation from high school, it's PV equals nRT. The pressure and volume are intensive variables. If you rearrange that so that you got, take the N that's on the nRT side, right, and divide through by that, then you've got P times V over N equals R times T. V over N would be an intensive variable, and temperature is an intensive variable. So for gases, there are 3 intensive variables that completely define any state of any gas. Give me the pressure, give me the temperature, give me the molar volume, and then I would know everything there is to know about that sample of gas. In fact, if I can assume it's an ideal gas, while gases need 3 variables to define them, temperature, pressure, and molar volume, if you tell me 2 of those 3 and that it is an ideal gas, I don't have to know all 3. I can calculate the 3rd from the other 2. If you give me the temperature and molar volume, then I can calculate the pressure in the sample and so forth. So you can define a state of a system by the number of variables that are possible. Remember when I told you about balancing equations, I told you there was only 2 variables that define a chemical reaction. And if you know the one of them, you will know the other one. Okay, that's how we balanced equations. When you get to physical chemistry, they'll teach you a thing called the Gibbs phase rule. And what it does, it answers the question. If I'm going into laboratory to make a measurement and I want to reproduce that measurement or tell somebody else across the world how they can do it, what is the minimum number of things I need to tell them? And the Gibbs phase rule tells you that. You're able to calculate the number of what they call then degrees of freedom, independent variables that you have to specify. And when I was trying to get this that balancing equation method published, I felt like I needed to do a proof to show that this method will always work. And so I did use the Gibbs phase rule, and it is true that with some stipulation, any equation can be balanced with only 2 coefficients. And sure enough, when you know one of them, you can know the other one as well. So the state of a system is going to be defined by its intensive variables, temperature, pressure, molar volume, things like that. And once you know these, you know exactly how to reproduce that system. And again, if you know some relationship, you reduce the number of independent variables necessary. That's what the Gibbs phase rule says. For every independent relationship, you subtract one off of that set of intensive variables. And that's how I reduced it from, n equations and n unknowns that they teach you in linear algebra down to just 2 for a chemical reaction. Because there's a law of conservation of mass. The mass has to be conserved during it. And you have to be able to identify each individual atom on each side of the equation. So that's another relationship. And when you take out all of those relationships, you're left with just 2 for a general chemical reaction. So it does work. Okay. Now, where does internal energy reside? It's in the intermolecular forces between the atoms and molecules that make up an object. So I'm thinking about now, I'm holding my fists up in front of me. This is one molecule, this is the other one. The attraction between those particles is an intermolecular force. If there's an intermolecular force, and we'll learn in Gen Chem 2, there is. Everything attracts everything else. So there is going to be an internal intermolecular force between particles. And so as you bring the molecules closer together, that force is going to go up, and there would be an amount of energy involved in those intermolecular interactions. That's part of the internal energy. So when I put heat energy into a sample of matter, that's one of the places it can go. It can go to increase the average separation between particles that are attracting each other. And it can vary, it gets absorbed in that intermolecular force. Now, we don't want this one to happen, but there's an intramolecular force, which is the force that holds an individual molecule together. We call those things covalent bonds that hold the molecules together. Now, we don't generally want to break them up. We could. If we kept putting heat energy into a molecule, we'll reach a temperature where it starts to decompose and breaks the bonds that hold the atoms together. So that is still also a part of internal energy. The intramolecular forces between particles and, intermolecular forces between particles, and the intramolecular forces within each individual particle. Now, what about energy? One of the things you always see is you see energy flow. You see it go from one place to another. It's not possible to imagine any measurement you could do and tell how much energy an object has, because it's got all kinds of energy. Remember, right at the bottom line, there's the Einstein relationship, E equals mc squared. So if you've got mass, you've got energy by virtue of the fact that you've got mass in the system. And so everything is going to possess some internal energy. How much? It turns out we can't ever really know that. Because remember, when way back in the beginning, one of the questions on one of the quizzes was, if you want to measure something, what do you have to know and define to have your measuring system? Well, you have to know how big your unit is. If I'm talking about a Celsius thermometer and a Fahrenheit thermometer, there is a size of the unit that makes that up. The other thing you have to know is what zero is. Zero of energy is undefined. I have a concept. There is I can take something and I can cool it down. I can take energy away from it by touching it to something colder. And I could just imagine that if I can take out energy, I keep taking it out. If I got to a point where there was none left, that would be my zero. Well, what would that be? Well, if it's true zero of energy, it means you can't have any mass, because mass has energy by E equals mc squared. So what is a state that has zero energy? Maybe nothing. I have not a clue. And so it's not going to be important to us, because we never see absolute energies. We only see when energy flows from one place to another. We can capture it and see how much energy that was, and then we know that system went from this energy level to this energy level, because it gave off the amount of energy we observed. So we see changes in energy, but that's all. We never see absolute energies. We only see changes in energy. Now, any process that takes me from state 1 to state 2 always involves the same energy change. And we're going to make really good use of this a little bit later. It doesn't matter how we do it. We can do it actually in the lab and measure it, like they did in Hess's law in the experimental part. But we can also take the numbers we got and calculate another energy. And we get the value we would get if we did the experiment. So you see, it doesn't matter whether you actually do the experiment and actually measure it. If you can imagine a process that you can use to go from state 1 to state 2, you're going to get the same answer somebody did by doing the experiment. You're going to get it just by doing a simple calculation, maybe. And so internal energy is a state function, which means all I got to do is subtract the two endpoints. Take the final energy and subtract off the initial energy, and I'll get the change in energy. So if I could do this subtraction, that's the way we would do it. Final energy minus initial energy gives me the change in energy. I can't do the subtraction on the right, but I can do the calculation. I can do the measurement on the left. I can measure the energy flow in a process. If it's a heat process, it's mass times specific heat times delta T. And so I can calculate that. So the E is a state function, and we said delta E is Q plus W. So I can measure heat flow, I can measure work. I add those two together, that's the internal energy change. While I can't do this subtraction, I can do this problem. I can go down here and measure heat flow in a process. All I got to do is just look at the thermometer and see what the temperature change was and what the mass and specific heat is. I can calculate that. I can take work as minus F times DL. I can measure the force. I can measure the distance it moved. I can measure these things on the right. I can't do the subtraction on the left, but it doesn't matter. I'll get the same value if I could do the subtraction that I get by measuring Q and W and adding them together. Now, let's look at a process where work isn't done. Now, how would I know work wasn't done? Did anybody pay attention? What has to happen for work to happen? A boundary has to move. So if the boundary doesn't move, no work gets done. So if I've got my process taking place and I got it all sealed up, you know, I got a gaseous reaction, or maybe I got methane and oxygen inside this container, and I've got the lid screwed on real tight. Okay, I've got methane and oxygen in there. I maybe have an pair of electrical leads going into it, and I can send a spark in there and ignite that. And it can explode inside that chamber. If the chamber doesn't break open, then no work was done. So that's a process where no work is done because the boundary didn't move. It didn't break open when I caused that explosion to take place inside. By the way, that device is called a bomb calorimeter for a real good reason. The jacket and the lid is so strong and sturdy. It's usually about a 1/4 inch stainless steel. And you can carry out some pretty big explosions inside without it actually exploding. But if it's put together on the top generally good strong threads, and at the top of those, where the two pieces seal, it has a rubber O-ring, and you tighten it down and compress it to that O-ring seals it off, so it can't um, escape out around the O-ring, and you're good. It'll work. But warning, you screw that lid on too loosely, so that when that explosion, the pressure builds up enough that it streams out past one little point on that O-ring. The O-ring will catch on fire and it will burn out, and it will explode. So when we use these devices in lab, you always put them behind the blast shield, and you get way away from there when you push the button to cause the reaction to take place inside. You don't want your bomb calorimeter to be just a bomb. You want it to hold it together, because you're depending on no boundary moving, and that causes the work to be zero. Now look what this does. If I make the work zero, then I drop the work term out. I've subscripted this Q as Q when the volume is constant. That little V means the volume is held constant. Now I can do that experiment. I just told you about it. I put my stuff in the reaction in this bomb calorimeter. I cause the reaction to take place. I measure the heat flow. Now, actually, you don't measure heat flow. You calculate it. Q is mass times specific heat times delta T. So I know the mass of the calorimeter and its contents. I know the specific heat of the calorimeter and its contents. I measure the temperature change. When I take the difference in the final and initial temperature, multiply by mass and specific heat, I calculate this Q at constant volume. So this is an easy number to do. Really, really easy. Now, once I've got that, I've got delta E. Okay? So I've got my methane and oxygen. I put it in the bomb calorimeter. I explode it, and I measure the heat flow at constant volume. That's delta E. And now, what's delta E? It's a state function. So that means anytime I take 1 mole of methane and burn it in oxygen, I will always get that change in E, no matter what, no matter how it's taking place. If I put it in your Bunsen burner and burn it out there, the heat that I measure burning out there is not going to be the internal energy. It's going to be a amount of energy we call the enthalpy. But what was the delta E change? Delta E is the same. If I go from 1 mole of methane to its equivalent carbon dioxide and water, I'm going to get the same value for delta E no matter how it's taken. So if I, one time in my life, I do methane and oxygen on a bomb calorimeter, I can calculate the Q at constant volume. I can put that in the back of the book. That's delta E for that process. And if I get, make up a number, 150 kilojoules. If I got 150 kilojoules for delta E, anytime you go from methane to oxygen and oxygen to carbon dioxide and water, that's going to be a change in delta E. It's a state function. Whether it's in the bomb calorimeter here that we can measure, or once I know the number, 150 kilojoules, it's the same. So what's the change in internal energy when you burn a mole of methane in your Bunsen burner? 150 kilojoules. What if you put methane in your car and explode it in your engine and drive your car? What's the change in delta E? It's the same, 150 kilojoules. What if I take one of these new fuel cells where it converts directly from a chemical reaction to electrical energy? What if I use methane as the fuel in the fuel cell and I burn 1 mole of it in the fuel cell? What's the change in delta E? 150 kilojoules. It's the same number. Remember, that's what we're getting at with state functions. That's the beauty of them. I only need to measure them once. Once I know it one time, I know it every time. And the only way, though, I can actually measure delta E is to do this, carry it out in a process where the work can't be done, and then measure the heat flow. And then once I know it once, I know it forever. And that's how we're getting delta E. Now, heat flow at constant pressure is also a state function. We call it enthalpy. It corrects for the fact that it is heat, delta E is Q plus W. I think I've got the derivation here, yeah. And so delta E is Q at constant pressure minus W, see. I'm carrying out a process at constant pressure, and I get delta E is Q plus W, doesn't matter, no matter what. But if I'm doing it at constant pressure, I'm talking about the heat flow at constant pressure, not the one we did just a while ago at constant volume. We're going to just hold the pressure constant, but not the volume. Then I have to put the work term in. Work is minus P delta V. And now I can rearrange this like this. E2 minus E1 is Q at constant pressure minus P2, P times V2 minus V1, that's delta V. Now, if I rearrange terms and just solve for the QP, I get this E2 plus PV2 minus E1 plus PV1 is Q at constant pressure. Now that looks like a state function. This value minus some other value, you get it by subtraction. At final minus initial, I get a change that's how we define a state function. So Q at constant pressure is a state function. If we define H as E plus PV, then this is H2 minus H1 is QP. So enthalpy function is defined as E plus PV. Now, let's think about what it is. If I've got a gaseous system, it's got energy by virtue of the fact that it's made of stuff that's got an internal energy. So there's an internal energy part of that gaseous system. But because it's a gaseous system, it also has the potential for work term. It has an energy by virtue of its pressure and volume. Remember on the ideal gas equation, PV equals nRT. So P times V is given by R times T, and at constant temperature, it's going to be determined by that R value. And R was in liters and atmospheres, it's 0.0821 liter atmospheres per mole per Kelvin. There's another value of R that we're going to have to learn and we use very often. It's R is 8.314 joules per mole per Kelvin. So the liters times atmospheres is also equivalent to energy in terms of joules. And you can actually use that as a conversion factor. 0.0821 liter atmospheres will equal to 8.314 joules. So the pressure and volume has an energy component in it. Pressure times volume is like energy. And that is the conversion between liter atmospheres and joules. If I wanted to do the conversion, I had 50 liter atmospheres, and I don't know how many joules that is. I'd take 50 liter atmospheres, conversion factor, liter atmospheres on the bottom, joules on the top, 8.314 with the joules and 0.0821 with the liter atmospheres, cancel out my units, and I use the conversion, just like before. So pressure times volume is energy. And I have to include that with the internal energy when I'm thinking about enthalpy. Enthalpy includes both. Now, lest you think that's not important, let me tell you a true story. I don't recall where it took place, but there was a graduate student that was using a high pressure tank of oxygen for an experiment. And he wanted to move the oxygen tank from one side of the lab room over to the other side of the lab room where he wanted to use the oxygen for a different experiment. So what he did was he just grabbed up that tank of oxygen and disconnected the hose from it on experiment 1. He leans it over, think now a 4-foot tall tank of oxygen with a regulator on top, got some valves and got a spigot where you can turn it off and on. And then it's got a place that you can attach a hose to your apparatus. So he detached the hose from his apparatus on this side of the lab, leaned the cylinder over and started dragging it across the room to the other side of the room where he wanted to put it. Well, it slipped out of his hand. When it slipped out of his hand, that big old massive regulator sitting on the top of the tank of oxygen broke off. When it broke off, the oxygen came out so fast and so hot, he was cremated on the spot. He was actually burned up. And that tank of oxygen shot like a rocket across the room, out through the concrete, the mortar, the plaster, the concrete blocks into the parking lot outside. That's how much energy a tank of gases contain. And whenever they're above a certain temperature and at high pressure, the gas heats on expansion instead of cooling. And that's what happens to oxygen. So we require, and since that terrible accident, federal law requires that anytime there's a gas cylinder in a lab room, it has to be tied down to the lab bench so it can't possibly fall over. And it's required that you take the regulator off, you turn off the valve that releases the gas, take the regulator off and put a protective steel cap over the top of the gas cylinder before you move it. And that would have protected that guy and saved his life. But the gruesome story was just to illustrate to you that this PV product is a very significant amount of energy. For any gas system, there's a lot of energy due to the fact that it's a gas. That's the reason why it's got that extra energy in it, because it's a gas. So this function takes that energy into account. It's made of two parts. The enthalpy is the internal energy, E, that we've discussed and we know about that, plus the pressure and times the volume of the gas sample. That becomes another part of the internal energy. Now, the heat flow when the pressure is constant is delta H. So if I carry out an experiment in a bomb calorimeter and measure the heat flow, I will measure delta E. And like I said, put it in the back of the book. I measure it once, I never need to measure it again. Now, suppose I take that methane and burn a mole of it in your Bunsen burner. That's at constant pressure. If I measure the heat flow that comes off when I burn that at constant pressure, that's delta H. And if I got 150 kilojoules for delta E, maybe I'd get 230 for delta H. I don't know. I've just made those numbers up. But the point is, if I measure this once, I never need to do it again. So again, if I measure my constant out there on the Bunsen burner, I can measure QP and I can calculate delta H. And now I know it. Now, what about taking that same mole of gas and putting it in the bomb calorimeter? And if I got out there, I don't know what I said, 330 kilojoules for delta H, let's say, by the Bunsen burner. What's delta H in the constant volume calorimeter experiment? It's still the same. It doesn't matter how you carry the process out. You do have to carry the process out once at constant pressure to get delta H. But once you've got it, you got it. Just like you have to carry out one experiment at constant volume to get delta E. But once you got it, you got it. And then it doesn't matter how you imagine the process taking place again. If it's in the bomb calorimeter, if it's in the Bunsen burner, if it's in the exploding balloon, if it's in this, your car engine, if it's in a fuel cell. It doesn't matter where it is, as long as the process is 1 mole of methane plus the balancing amount of oxygen goes to carbon dioxide and water with the same balanced equation. As long as that equation is the same, the delta H and delta E are always the same. Does that make sense? I'm making a really, really critical, important point, what a state function is and how they're so important. Once I know what it is, I never have to measure it again. I just measure it once. Now, if I look at the relationship between delta E and delta H, remember H is E plus PV. So a change in delta H and H, or a change in E, is the change in E plus the change in the PV product. And I can then substitute in Q at constant pressure for delta H and Q at constant volume for delta E. If I subtract them this way, I get delta PV, which would be P delta V. And so this is the relationship between the heat flow at constant pressure, the heat flow at constant volume, and the work that's done. So that's going back to our Q plus W, the way we defined it way back in the beginning. So the heat flow at constant pressure is not generally equal to the heat flow at constant volume. It's often more negative. Okay. E and H both depend on the type of substance present. That is, if you've got gaseous water, if you've got liquid water, if you've got solid water, all three of these would have a different value for both the E and the H within the sample, internal energy and enthalpy within that sample. It does depend on the phase of the matter. And, you know, I told you these things are going to be in the back of your book. It'll be very, very critical that you notice the state symbol, because you'll have three different numbers for water in the back of your book for, say, for example, its enthalpy value would have three different values depending on whether it's gaseous, liquid, or solid. They depend on the amount of substance. And what do we call that? Those are extensive. It's an extensive variable. If you got a mole or a gram, you get a different number. Now, you learn from Hess's law also that if you turn a reaction around, you change what you've defined as the reactants and products. So when you do the subtraction, if the reaction is exothermic in one direction, you turn it around, it becomes endothermic. So you change the sign of the heat flow for delta E or delta H when you change the direction of the reaction. If you reverse the direction, you also switch signs. If it's negative, it becomes positive. If it's positive, it becomes negative. Okay. Now, most of the time in the laboratory situation, it's much easier to hold pressure constant than it is to hold volume constant. Now, volume, I told you about the bomb calorimeter. That works very well as long as everything, reactants and products, are gaseous. But if you've got liquids and solids have a unique density at any temperature. So if I change the amount of a substance in there, I'm going to cause the volume to change. And if you think of it in the reverse, if I've got a liquid and I put pressure on it, like when you push your brakes on your car, the whole braking system is filled with brake fluid. That's a liquid. And when you push on that brake pedal, you put pressure on that liquid, and it transfers the same pressure to all your wheel cylinders and causes the brakes to come out and slow the car down. And it depends on the fact that when you push on a liquid, you can't compress it. If you could just compress the liquid, like for example, you get you get air in your gas line, in your brake lines. You push on the brakes and you don't stop so good. And in the old days when it wasn't all electronic, you could actually feel it spongy when you put your foot on the brake. The brake pedal would feel spongy. It feels like you push it in before it ever did anything. Well, that's what happens. You put the pressure on there, but you had gases in there. So you could compress that gas and didn't push that out to the wheel cylinder to cause you to stop. And you fix that by bleeding the air out of your gas line, brake lines. Well, now things are different. You probably could get by with a little gas in there because you use a you use an electrical system instead of a mechanical system to apply the brake pressure, but that's all another story. Okay, but you can't hold volume constant generally if you've got liquids and solids, because if I take the density of the reactants, all of them, and the density of all the products, if the products are more dense, then what's going to happen is the volume's going to decrease, and there's nothing you can do to stop that. You can't get in there and grab onto the molecules and keep them from getting closer together. That's just the way it's going to be. And similarly, if you've got something going from a high density reactant set to a lower density product set, then you're going to expand volume. And you would have to have thousands of atmospheres of pressure to resist that volume change. And most of the time, if that happens in your quote bomb calorimeter, it's going to be a bomb and not a calorimeter in those cases. So it's just not possible to hold volume constant when you're dealing with liquids and solids. So for us, the function we're most interested in is the enthalpy function, because we can hold pressure constant no matter if you go from dense liquids to less dense liquids or vice versa, it won't matter. Pressure is held constant in the lab because it doesn't generally change in nature until we're done. So delta H is much easier to use than delta E. That's the better of the two functions. We know one, we can calculate the other one. Remember, delta H is delta E plus delta PV. I can measure delta H and calculate delta E if I can't actually measure delta E easily in the lab. Now, heat in a sample depends on how much sample you got. It depends on how much it takes to heat one mass of that sample 1 degree, and it depends on the temperature change. This is all quite logical. The more stuff you've got, the more heat it's going to take. The bigger the heat capacity, the more energy it takes to raise it 1 degree, the more energy you're going to take. If you heat it through 5 degrees or 10 degrees is going to take twice as much. So this is the relationship we use in the lab to actually calculate heat flow. It's the mass times the specific heat capacity of the system times delta T. Now, if you're doing the same calorimeter experiment over and over and over again, you're probably going to use the same apparatus. So rather than measure the mass and the specific heat every time you use it, what we do is we take something, typically what we use is a compound called benzoic acid that has a very accurately known heat of combustion. So I take that benzoic acid and I can put that in my bomb calorimeter and set it in the bucket and put the amount of water in the bucket and do all of the experiment, and I can measure the temperature change. Since I know how much heat is, I know this CP, the heat capacity of the calorimeter, which is mass times specific heat. So as long as I use the same bucket, the same bomb inside it, the same amount of water, generally the bucket will come with a little line on the top. You fill to that line every time. So you're going to have the same amount of water in it every time. So I put the benzoic acid tablet in it, burn it, and measure this temperature change, divide the heat I put in by the temperature change, and I get this CP number. And then I can just put that on the bottom of the bucket. They usually come scratched in on the bottom of the bucket, what the heat capacity of the system is. And so that way, I only measure delta T. I never have to weigh things. I never have to go look up what the heat capacities of the different metals and stuff that's inside the calorimeter. I don't have to do any of that. I just calibrate it once by putting a gram of benzoic acid in and measuring the temperature change. And then I can get CP for the calorimeter. And it'll be in joules per degree. Now, if you've got something heated by something colder, then heat's going to flow between them. The same number of joules that's going to come out of the hot object is going to be the amount that goes into the cold object. And so the mass times specific heat times temperature change in the cold object would be equal to the mass times the specific heat times the temperature change in the hot object. So that's the calorimeter relationship between heating something and a calorimeter. The heat that you take to vaporize a mold is called the heat of vaporization. You might need to remove heat from something to freeze it, and that's called the heat of fusion. And now, this is funny. Whenever you cool something, you take the heat out of it, right? You take heat coming out is going to make it colder, but heat coming out has what sign? It's negative. Heat coming out is negative. So that means the process is exothermic. I've heard people say some stupid stuff like this. Well, since water gives off heat when it freezes, hot water would freeze colder faster than cold water. Well, no, it won't. You can't freeze hot water. When you have to first cool that hot water down to zero before it can freeze. So that's totally illogical and stupid. But I've heard smart people say things like that because it's exothermic. Water gives off heat when it freezes. It absolutely does not. I came from the farm. People say cows give milk. I know better. Cows don't give milk. You have to go in there and take it from them. And that's the same way when you freeze water. Water doesn't give off heat when you freeze it. You have to take heat out of it to make it freeze. So watch people that think they're smart. They sometimes say some stupid stuff. And that's one of the stupid stuff that people say. And I've heard people try to justify it. And there's some truth to that. Like, for example, if you take water and heat it up, water contains gases dissolved in it. And we're going to learn in Gen Chem 2, anything dissolved in water makes it freeze at a lower temperature. So if you took water that came from your hot water heater and cooled it down to 0 degrees, it's probably got less dissolved gas in it. And then you take regular water that hasn't been heated and freeze the two of those, it might be that the pure water would freeze before the water that still had some gases dissolved in it. So the water that had been hot would freeze before water that had never been heated, because the water that had never been heated will have a little bit of dissolved air in it and have a little slightly bit colder, a lower freezing point. But that's very small. And if you take hot water directly out of the tap and cold water out of the tap, and you put both in your freezing trays and watch them every once in a while, I'll bet you money the one that came out of the cold water tap will be iced before the other one will. Not quite going to happen. Okay. Now here's some problems with this. I think this might be a good time to just kind of stop and take a breather. So what, let's pick back up at maybe 9:25 and give you guys a chance to take a little break and give me a chance to get a little coffee. And let's go back to, okay. I think this is where we were we're starting to look at some problems involving the concepts that we've just been discussing. And uh, let's, some of these are intended to be exercises in the units to make sure you get your units right. So I want to emphasize again that generally if you follow units through your calculations, if the units you get for on your paper when you did the unit analysis, if that's the same unit that's in the problem, you probably got the number right. And it's important to be sure to have that set of units so that you can follow that through the calculation and see that the unit you get when you look at your calculator, you're just going to get the number. You will have to put the unit in, and you can do that. And if you've done unit analysis, you can make sure that your units all canceled and during the calculation. So here we go. How much energy is required to stop a 10-gram object moving at 250 meters per second? Okay, I put these all into convenient units. The energy to stop would be to absorb the kinetic energy of the object. So we're going to have to solve the kinetic energy. That's 1/2 mv squared. So now, 1/2 is 0.5. If I've got a 10-gram object, that's 0.010 kilograms. And remember, unit has to be in kilograms. I did give you the velocity in meters per second, so that is the correct unit. So when I do this math, I get 312 on my calculator. But I put in SI units over here. I put in kilograms. I put in meters. I put in seconds. That means the SI unit I put in here will give me the SI unit I'm calculating here. What's the SI unit for energy? It's joules. Now, it is true that joules is kilograms meter squared per second squared. So you can deconvolve this unit like that and come out with joules. Or you can just be confident that if you put SI units in for mass, SI unit in for distance, SI unit in for time, you will get the SI unit for what you're calculating. E, that's joules. So I seldom actually do this kind of deconvolving. I always just make sure that I'm putting in SI units on all of the things I'm doing calculations. Everywhere I put a number in, I make sure I put the SI unit for that number. So I didn't put 10 grams in here. I knew I had to have kilograms. So I changed the 10 grams to kilograms. And then if this had been given in feet per second or feet per hour or whatever, then I would, or miles per hour, I would have had to convert miles all the way to meters. I would have converted hours all the way to seconds. And then I would divide those in meters per second. I would have now my distance in meters, my time in seconds. I would be confident I'd get joules. So it's important that you use SI units. And then you don't have to do this. You don't have to memorize that kinetic energy is kilograms meters squared per second squared. You don't, as long as you put the units in SI units, the numbers in SI units, the answer you get will be in SI units. What mass of water could be vaporized by this much energy? Heat of vaporization of water is 2,260 joules per gram. It's a very high heat of vaporization. That's really, really good. I don't know that I told you this, but maybe I did when we were talking about the energy in the atmosphere and the carbon dioxide greenhouse effect and things like that. It's implied that a lot of the energy in the atmosphere is caused by the carbon dioxide in the atmosphere. We saw that that's limited and it's already done. But how do you get energy transferred from one place on the earth to another? It's by moving water. I told you when the sun shines on the ocean, it's going to vaporize water to gaseous water. Gaseous water has a molecular weight of 18. Air has a molecular weight of 29. That gaseous water is going to continue to rise off the surface of the earth all the time the sun is shining on that ocean water. So that water is going up as vapor into the atmosphere. Those gaseous water vapor is swept along with the clouds, swept along with the air. And when it gets over land, then it can get into regions where it starts to cool and form little water droplets. And as it forms those little water droplets, it releases the energy that it's absorbed way back over here. And you probably don't remember the number, but I think I've told you this. Over a 1 square mile area, a 1-inch rainfall has an amount of energy equal to 2.5 atomic bombs, like we dropped on the end of World War II. 2.5 atomic bombs for 1 square mile area, a 1-inch rainfall. So generally when we have storms come in, they might cover the whole state and they might drop 3 or 4 inches of rain or maybe a foot. We had a system here in Bowling Green 8 or 10 years ago maybe that it rained and the clouds just sat over top of Bowling Green, rained for about a week. And at my house, I could see the water from the river. It backed up all the way to there. Now, we never got any water damage or floods, but it really ruined lots of houses, and it was a disaster. And that is, the water was one thing, but all of that energy was transported as well. So most of the energy that's transported from one place to the earth to the other that keeps the earth's moderate temperature it's done by water vapor. And so let's look at how much water it would take to stop this object. 10 grams might be the size of a bullet, and 250 meters per second could perhaps be close to muzzle velocity. Okay, so we do the calculation. There's an amount of joules we got up here. And now let's use the conversion. You get 2,260 joules for 1 gram. Do our conversion factor method. We get 0.138 grams of water. There's 20 drops of water in a gram. So that's about 3 drops. The amount of energy that was dissipated by this object being stopped could have just vaporized 3 drops of water, and that would have used it all up. That's how much energy vaporization of water does. Now let's look at a system has a heat capacity. It's 20.8 joules per degree Celsius. It's heated at constant atmosphere pressure from 25 degrees to 50. As the volume increases from 24.4 liters to 26.5 liters, calculate all these functions, Q, W, delta E, and delta H. All right, so let's start working with it. Q is Cp times delta T. I know what the heat capacity is. I know what the temperature change is, so I can do that calculation. So it's 20.8 joules per Celsius, and the temperature changes from 50 to 25, and that gives me the heat flow. Now, by the way, I've emphasized the sign here, but I don't want you ever to do this, and this is what books encourage. You take the final minus the initial and you subtract them, and that gives you the sign. Look, anytime you do a subtraction, do what they told you to do in 3rd grade. Take the little number and subtract it from the big number. I don't care whether it's initial or final. It don't matter to me. All I want to know is what's that difference. So take the big number and subtract the little number. Now, when you get done, you're going to get a heat flow. Ask yourself, what should be the sign of that heat flow? Okay, so what had to happen when you take something and it's at 25 degrees and you want to put it up to 50 degrees. What do you have to do? Do you have to put heat in or take it out? That's obvious, isn't it? So when you ask it that way, when you put heat into that object to raise its temperature from 25 to 50, what is the sign for anything going in? It's plus. Okay, so how am I going to get the sign of my delta T, of my heat flow? I'm going to look at the change in temperature. And I'm going to note where the thermometer is. If it's talking about the temperature inside a system, the thermometer is inside the system. So if the thermometer is inside the system and the temperature goes up, heat went in. All right? That's how you have to make the temperature go up. You have to put heat in. All right? Now, what if the temperature dropped? The temperature went from 50 down to 25. What would I do to do that? Well, heat would have to come out. I would have to remove heat from the system, and heat coming out of the system is what sign? Negative. So you see, by getting the sign of the temperature change I actually observe and noting where the thermometer is. Now, it makes a difference whether the thermometer is inside the system or outside in the surroundings. It's going to be one of those two places. We can tell from context where that thermometer is. And then we can tell whether heat went to where the thermometer is or not. If heat goes to wherever the thermometer is, the temperature is going up. So if temperature goes up, then I know heat flowed into the region where the thermometer was. And I can get the sign. So don't worry about taking T2 minus T1, initial minus final minus initial, and let that give you the sign. That's where people make mistakes. And that's going to always be one of the bad choices, usually on quizzes or exams. Now, let's look at what it's at. It's heated at constant pressure. What did that tell me? The heat flow at constant pressure is which of the functions, E or H? That's right, it's H. Heat flow at constant pressure is H. I measured the heat flow at constant pressure to be plus 520 joules. So that's also the value of delta H. Now, what's the work? Well, it's P times delta V. So the pressure was 1 atmosphere, and it changed from 24.6 to 26.5. Now, I want to go over here to my paper so you can watch this. I want to show you something. Now, get where I can see. I've got a system that looks like this. Now, I'm going to call this my initial state here. And the volume increased from, so it started here. And this was 24.4. It's 24.4 liters in the initial state. Now I'm going to look over here, and I need to try to draw a very similar picture if I can. And it is at the final state. It's at 26.5. Now, you look at these two pictures and you tell me, in going from here to here, now imagining out here, the pressure is setting out here. That's the force acting down. So when this goes from this state to this state, did the system push the atmosphere back, or did the atmosphere compress the system going from here to here? Well, the system pushed the atmosphere back. So work came out of the system. Came out of the system. Work coming out of the system is what sign? Anything coming out is what? Work is going to be a negative value. Now, I didn't need to take V2 minus V1 and change the sign. Remember, what people are going to say is, well, W is minus P delta V. So they're going to put in V2 is 26.5 minus 24.4. That's a positive number. Positive and a negative number gives me a negative number. Okay, that's true. That's correct. Absolutely correct. But what if you screwed up and put the numbers in backwards? I could look at this picture and I can look at that picture and I can tell work had to come out of the system to push the atmosphere back. Work is out. Work coming out, anything coming out is negative. The sign of that workflow should be negative. And so you should not depend on that formula to give you the sign. So I'm not going to do that. Okay. Now, okay. Need to start I got to get back to where I was because I had to shut it down to get out of there. Okay, so there we go. We calculated the value of minus 2.13 liter atmospheres. Remember, atmospheres, pressure, volume is liters. So this is liter atmospheres is the energy unit. Now, if I take that 2.1, multiply by 8.314, and divide by 0.0821, that's the conversion factor. Remember, we got R in two different units. R is 0.0821 liter atmospheres. It's also 8.314 joules. So 0.08 liter atmospheres is 8.314 joules. So that's our conversion factor, and this comes out to be negative 213 joules. And the negative sign was because we saw in our little picture on the right, we saw the volume increase during the reaction, which meant the system had to push the surroundings back to accommodate that volume increase, and work came out of the system. So now I've got the value of delta E and delta H from the experiment, so I can plug the numbers in and solve for delta H, delta E. Delta H is delta E plus delta PV. So there's the delta H we calculated earlier. And here is the volume of the work term was negative 213 joules. So I put the signs in and check everything, see is this correct? Well, now, it is correct, but how do I know? Almost always, in fact, I cannot think of a single incident in which this isn't true. The sign of delta E and delta H are almost always the same. So up here, I got the value of delta E, delta H confidently, that is positive 520. I might not know that this is going to be 307, but I do feel very confident since the Q flow and delta H were negative, I'm sorry, or both positive, then delta E should be positive as well. And there's not a good way to check it other than that. But I think that's, like I said, I don't know of a single example where that isn't true. How much heat is needed to heat 150 grams of iron with this specific heat from 0 to 300 Celsius, 300 Kelvin? Okay, got to have the temperature units the same, so you can make them both Celsius or both Kelvins. It wouldn't matter. The size of a unit is the same in both temperature scales. But what I did is I converted the Kelvins back to Celsius by subtracting 273.15 from 300. I get 26.85. And I did that because the specific heat was given in degrees Celsius. So I wanted these units to be in degrees Celsius. And again, we want to calculate the heat flow. Now, let's pause right here for a moment. The heat flow, I got the number. I put that on my calculator. It said 1810, but it didn't say joules. Do I know that it should be joules? Yes, I do, because it's calculating a heat, an energy. Energy and SI units are supposed to be joules. I'm looking here at the specific heat. Yep, it was given in joules. So that makes sense. I've got this all calculated, and I should get the SI unit for joules, and it's this. What about the sign? Is that right? Again, I'm going to look at it. Here, the sample started out at 0, and it went up to 26.5 degrees. Did I have to put heat into the iron or take it out to raise its temperature? Obviously, I had to put it in. Okay, putting in is what sign? Positive. So again, I'm not going to worry about whether I got this sign correct or not. I'm generally going to subtract the little number from the big number, and I'm going to apply the sign myself rather than depend on the sign of my delta T to give me the sign of Q. Because in some cases, we had a negative sign out here, and negative times a negative would give the positive. So I don't allow myself the luxury of making that mistake. I'm going to assign the sign myself because it means I did take it into account. I didn't just blindly let something give me the sign. I gave it the sign I knew it had to have. That's much better than trying to depend on some formula. Okay, what would be the final temperature if 50 grams of iron at 100 degrees C is dropped into 150 grams of water with this specific heat at 0 degrees? Well, heat's going to come out of the hot one into the cold one. And so I'm going to write it this way. The book says heat gain equals negative heat loss. Now that's really true. That is exactly true. But I'm going to make sure every time I put this equation in, I get a positive number. So I'm going to make the heat lost a positive number and the heat gained a positive number. I'm just going to look at absolute values. That's all that's important. And I don't want that negative sign in there to be a negative. So the absolute value of the heat lost will equal the absolute value of the heat gain. That is a true statement too. Now let's plug it in. Now here's what I know. The hot object was at 100 degrees. The cold object was at 0 degrees. The final temperature is between those two numbers. It's some value T. The value T is less than 100 and more than 0. So when I'm looking at the heat lost by the iron at 50 grams of iron, it's 4.45 joules per gram per Celsius. And the temperature change is from 100 to T. And I know that's a positive number because I know the final temperature has to be less than 100. So that I didn't put T final, which would have been T, minus T initial, which would have been 100, and then a negative sign out here. There's just too many ways to screw up signs to do that. Don't do that, please. I know the final temperature is less than 100, so this is 100 minus T. That'll be a positive number. Then I look over on the water side. The water side is going to gain the heat, but this will be a positive number. There's the 150 grams. There's 4.184 joules per gram per Celsius for water. The temperature final of water is T, and that's bigger than 0. So it's T minus 0. Now this one is kind of a trivial case because it started at 0, but this could have been 22 degrees Celsius. And then that would have been a 22. T is still going to be above the low temperature and below the high temperature. So this guarantees the left-hand side is a positive number. This guarantees the right-hand side is a positive number. Now I can set them equal to and do the math. And I don't have to have that minus sign out here, has to carry through inside here and have minus a plus. No. Don't do that. There's the math. Multiply all these together and times t here, and then multiply these together. You get 627t minus 0. I went ahead and put the 0 in. I can solve that for t. And when I get that, I get 3.46. Now, does that make sense? When you get an answer, ask yourself, does that make sense? I'm looking at this and I'm saying, okay, let's think about it. Is the temperature less than 100? Yes. Is the temperature greater than 0? Yes. Which is it closer to? It's closer to the 0, isn't it? Well, look here. I've got 150 grams of water with a very high heat capacity. So I'm going to have a lot of this, which means I'm going to get a smaller number out there. So yes, that makes sense. That it would be closer to 0 than it would be to 100. Now, if I'd had 150 grams of iron at that temperature with 50 grams of water, I don't know. I really need to multiply the mass times the specific heat to see which one it would be closest to. But in this case, it's obvious. I've got more water and I've got a higher heat capacity for water. So the temperature is going to be closer to the water value than it would be to the other one. Logically, I can check myself. Is it exactly 3.46? Well, if I didn't make a mistake, it is. If I did make a mistake and it still satisfies all of those, I might not know. If I'm looking at multiple choice answers, if there's another answer in there that's, 6.34, then I couldn't distinguish between those two. I couldn't. But if I had one in there that's 98.2, I know that's wrong. I don't even have to worry about that response. I can mark that off right now because it can't be closest to the water, to the iron. It has a lower amount and lower heat capacity, much lower. All right, here's a checkpoint for you. This reaction is occurring in two experiments. We're starting out with 1 mole of nitrogen gas, 3 moles of hydrogen, and we're going to 2 moles of ammonia in the reaction. And I've got a heat capacity for the calorimeter and its contents. So here's my first experiment. I've got 620.4 milliliters of this gas, and it's at 25 degrees. Notice where the thermometer is. The thermometer is not inside with the system. It's outside in the calorimeter, which is the more usual way of setup. Now, that's my initial state. In my final state, look what happened. Volume is still constant. But the temperature did go up from 25 to 25.225 degrees Celsius out here. Now you tell me, when I go from the initial state to the final state, the temperature in the thermometer outside the system went up. Did heat flow out of the system into where the thermometer is, or did it go the other way? Yeah, it went to outside. The heat flow, is that negative or positive? That's right. Anything coming out is negative. Okay, let's look at experiment 2. Now, experiment 2, we're going to hold the pressure constant. We start out at the same place, 620.4 milliliters of my gases at 25 degrees Celsius, and 1 atmosphere pressure, I'm assuming, or constant pressure. Don't need to know what it is. Now, but if the pressure is constant, I went from 3 plus 1 is 4 moles of gas in the beginning to 2 moles of gas. What's going to happen to the volume? It's going to go down. It's going to look like that. And here are the numbers. It's 310.4 milliliters, and the temperature is at 25.238 out here. Now, these are real numbers that really would have happened in this experiment. So here's an experiment. The number 1 is an experiment at constant volume. Number 2 is an experiment at constant pressure. So now let's think. I'm going to calculate Q for each case. Number 1 is Q at constant volume. What's that equal to? No, I'm not going to tell you. Go look it up. We just talked about it. This one's going to be at constant pressure. Q at constant pressure. It's CP delta T. So we got the heat flow. We got the temperature change. So we know what the number is. This one's going to be Q at constant volume with a sign that we can assign here. This is going to be Q at constant pressure with a sign that we can assign from here. And then what is this equal to? What I want you to do is tell me what the value for experiment 1 is delta H, delta E, Q, and W, and experiment in state 2. What would that be equal to? Okay. Now I'm going to actually do the checkpoint with you. This would be a really good exercise for you, but I told you I'll work through the checkpoints with you. So let's stop this, get it where I can see it. So now we've got for experiment 1, I know Q is going to be constant volume, and that's going to be the CP of the calorimeter times delta T. And I'm going to look at, and I'm going to say my delta T, I'm not doing initial and final. CP is 24.55 joules per Kelvin, and joules per Celsius. And the temperature change. The temperature change, my big number is 25.225 minus 25.000. Let's do my math on the calculator here. So it's 0.225 minus 0. Okay, that's 0.225 is my delta T. I want to multiply it by 24.55. That's not a point there. That's 24.55. So times 2455. I get Q is equal to 552.375. The units are going, that was in joules per degree, and so this is going to be in degrees. Now, is the sign positive or negative? Well, I'm looking back now at the thermometer. In the final state, the temperature was higher. So this was a bigger number, and it's outside the system. So heat flowed from the system to the surroundings. That's out of the system. That's negative. So the heat flow at constant volume is minus that. Now that's also equal to delta E. Sorry, heat flow at constant volume is delta E. So on my down here when I'm doing my answers, experiment 1, the delta H, I don't know yet. The delta E, I do know. Delta E is equal to the heat flow at constant volume, so that's going to be minus 552. I'm not going to carry all those digits across. I'm just going to round off to there, 552 joules. And then Q is also minus 552. And work is equal to 0 because it's a constant volume. Anything at constant volume, no boundaries move. Look at the pictures. Boundaries are the same on both sides for my system. So I know E and Q and W in experiment 1. Now let's go to experiment 2. And in experiment 2, what do we have? Okay, we had Q this time measured at constant pressure. It's still going to be CP delta T. The CP is 24.55. The temperature change is 238 for this one. It's 25.238 is the big number. The small number is 25.000. So Now, when I do this math, I'm going to take 0.238 and multiply by that. So 0.238 times 2455. That's 584.29. So this is 584.29 and joules. And now what's the sign? Again, I'm looking back at the picture. The temperature final with the thermometer outside the system was higher than it was before. So heat came out of the system to where the thermometer was. And when heat comes out of the system to the thermometer, that's heat coming out. So that's negative also. The heat flow is negative. And now Q at constant pressure, that's equal to delta H. So delta H is also minus 584 kilojoules. Okay, so now I can get all of my answers because delta H is a state function. I measure it in the second experiment. And in the second experiment, it's 584, minus 584. What is delta H in the first experiment? I couldn't measure it, but I know what it is. It's a state function. I started with 1 mole of ammonia and 3 moles of hydrogen, and I went to 2 moles of ammonia in both cases. I had the same starting point and the same ending point. So that is a state function. I measured the Q at constant pressure in experiment 2. That gave me the delta H both in experiment 2 and experiment 1. So I know the number. When I went to the delta E value, I got that in experiment 1. But since delta E is a state function, it's also the same value in experiment 2. So now I've got everything except the Q in experiment 2. So delta H is equal to delta E plus P delta V, and delta H is equal to delta E minus the work, minus P delta V is work, so P delta V is minus work. So the work is going to be equal to delta E minus delta H. Okay, so what do we get for delta E? We got delta E was negative 552 minus the delta H, we get minus 584. So that's positive, so 584 minus 552 is going to be positive. And now let's see, what's the value? 584 minus 552 gives me plus 32 joules. Now I've calculated the sign here. Let's look at our example and see if this makes everything seem good. Let's see. I need to escape out of that, and I need to go back to a screen share with you. Now I want you to look at what we got. We got our numbers that we can put into here, but I'm looking at the work. Here's no work was done here, no volume change. Work is done here. Look at the picture. Did the system push the atmosphere back, or did the atmosphere push in on the system? When I went from this to this, you see the atmosphere pushed in, didn't it? That did work on the system. What's the sign of something going in? Positive. So we should get a positive sign, and that's what we got. We got plus 32 joules, and that is consistent with the picture we see up here. Now, I would believe the picture over what I did over here, because if I didn't get a positive value for work, I'd go back and see if I made a mistake when I did the calculation. I probably did somewhere. Okay, so this is a really good exercise. it shows you how that you can look at the pictures and tell what the sign of the heat flow would be. You can look at the pictures and see what the sign of the work should be. And you can look at the pictures and tell whether the work should be 0 or not. And if volume didn't change, work's 0. And that's what we saw in experiment 1. Okay? So this is a really, really good checkpoint problem. Okay, I've got to go. I'm going to have to get, this is all done by hyperlink. So if I don't link from here, I'll go to the wrong place in there. Now, I argued earlier that I couldn't define 0 for energy or enthalpy. I do know how to define an absolute 0 of temperature, and we talked about that. That's the point where there's absolutely no randomness in the motion of the molecules that make up the system. That would be a state of temperature equal to 0. And we could do all kinds of philosophical things here, but I'll pass on that. If the lowest temperature that you've got is absolute 0, why is it absolute 0? Because there's nothing colder. How do you get heat out of something to cool it down? You have to touch it with something colder. If there's nothing colder than that, then there's no way to transfer heat away. That's your 0. Now, the philosophical thing might be, what if everything in the whole universe were 25 degrees? What's the lowest temperature anything in the universe could ever be? 25 degrees. So in that case, what we were calling 25 degrees would be absolute 0 if nothing else in the whole universe could ever be colder than that. Okay? So it's philosophical when I say, what does that mean? I don't know that I know what that means. I just know that for temperature, it means the molecules are perfectly ordered and perfectly complete, perfect order. And that's how we define absolute 0 thermodynamically. Remember, we use Charles' law to predict absolute 0 when we cool a gas down and watch its volume get smaller. We extrapolate to when the volume would go to 0, and that was our absolute 0. So we can use gas laws as a way of defining absolute 0. Well, since we're going to know, we do know that the temperature is the randomness in the motion. When we're cooling something down, we're taking away the randomness. What's the limit of no randomness? It's a perfectly ordered substance. That is the way we define temperature, and our temperature 0. It's called the third law of thermodynamics. And what it says is that everything has a perfectly ordered structure at absolute 0 temperature. And it does turn out that those two predict exactly the same value if you go from the randomness at 25 degrees to no order. You would do that at minus 273.15 degrees Celsius. So the two do come together, two different ways of defining absolute 0 if you take the third law of thermodynamics as the defining relationship for temperature. You get the same value. But there's no meaningful 0 for energy. What does it mean to say something has no energy? Again, I go back to the argument with Einstein's theory. Einstein said E equals mc squared. So if you had no energy, you couldn't have mass either. If you can't have mass, if you can't have something, some substance, some physical substance present, how can you define a value for something when there's nothing? See? So there's no way you can really define a meaningful 0 for energy. I can't imagine an absolute energy, but in our world, it doesn't matter. All we're ever going to see is changes in energy. We're going to see energy flow out of this into that. And we can calculate how much energy went from this to that. That's not a big deal. We can measure differences in energy. That's perfectly observable to us. But absolute values are not. And we can get around this problem. You remember a while ago I said, talking about my coffee cup, I could say it could be on my desk here, or I could set it down on the floor. If I put it down there on the floor and never get out of this room, then that floor value isn't zero, but for every practical purpose, I could call that zero. And everywhere I move my coffee cup, anywhere in this environment, I could see how much energy is involved, how much energy would change just by measuring from what I called zero. Well, we can do the same thing with energy. We can't define a system that has no energy, but you can imagine there is one. I don't know what it is, but if I knew what that true zero was, I could configure my system to be like that, and I could call it zero. I could then mark off units the size of a joule, and I could again get a value of, I could just count the units from here up to here. That would give me the energy of state one. And I could do the same thing for state two. I could just go from this true zero. I could count them all up. I'd have a value for state two. If I wanted to get the change from state one to state two, I could take state two minus state one and take this distance here and subtract off this distance. I would be left with this distance. That would be my change in going from state one to state two. And I'd do it by subtraction. I'd take the number of units I counted from the ground state to state two, and the number of units I counted from state one up to state, from zero to state one, subtract the two numbers, and I would get this number here. Okay, if I had a true zero. What if I don't have a true zero, but I've got something that everybody in the world could define and agree on? We could come together and say, anytime I have this configuration, we're going to call that zero for energy. Now, since I know what this looks like, I can add joule units onto that scale and count them up from this reference zero up to state one. I could count the units from reference zero up to state two. Now I could subtract those two numbers and get this one. But look, I got the same value here as I got over here. Whether I use a true zero or whether I use a reference zero is no difference at all when it comes to calculating the energy flow or the change in heat or change in enthalpy, any state function. I can use a reference zero that defines that system, and I'm good. That's what we do. Now, what we call our standard zero. Okay, what do chemists work with? Well, indirectly elements, right? If you're dealing with compounds, you just make the compounds out of the elements. So the basic matter for chemists is elements, the way you would find them on the periodic chart, the natural phase of the elements. Remember, on the periodic chart, there's two liquids, there's a few gases, and most of the rest of them are solids. So we take the natural phase for that element at 1 atmosphere pressure and some reference temperature. In this country, we use 25 degrees Celsius as our reference temperature. In Europe, I think they use 20 degrees Celsius. But it doesn't matter as long as we're defining them. If I know I've got European data, all I'm going to do is I'm going to take their data and the heat capacity of each one of these substances and see how much energy I would have to put in to go from their value at 20 degrees to a value I want to use as a reference of 25 degrees. So I could convert their data to 25 degrees, and my colleagues in Europe could correct our data to their standard state of 20 degrees, and then we're both going to get the same answer when we get through. It won't matter at all then. Okay, so you're going to take the heat absorbed from 1 mole of a compound formed from its elements in their standard state as what we call the enthalpy of formation of the compound. For example, if I'm doing barium phosphate. Now, remember when we were looking at combination reactions, I said that this was one of the possible ways to combine things, but we never could do it. Well, we can't do it. We can't react barium and phosphorus and oxygen. These are their standard state values. Barium is solid at room temperature. Phosphorus is tetraatomic. It's like a little tetrahedron with 4 phosphorus atoms stuck together. That's the way you find phosphorus at room temperature and pressure. Oxygen is always gaseous at 25 degrees and 1 atmosphere pressure. So these are the standards for the elements. I've balanced it in a way that gave me 1 mole of product. And the energy of that reaction, we're going to put in the back of the book as our energy of formation of barium phosphate. It would be for this reaction. Doesn't matter that we can't carry out that reaction. We can carry out other reactions and do the same thing. This thing is going to take barium and phosphorus. It would make barium phosphide. It would make barium oxide, and it would make probably diphosphorus pentoxide would be the oxide of phosphorus that you would form. And then you could take those forms and mix them together in ways that you could make barium phosphate out of that. So there's ways of making barium phosphate even if you made the real products that would form between these elements. But the whole point I'm making is it doesn't matter how you get this. You can do it in one of the real ways you could measure it, or you could imagine this reaction taking place, and this is the energy of that imagined reaction. But now, this has an advantage. This is state 2. This is state 1. What's the energy of state 1? That's my reference. That's 0. All of this stuff is now 0. So you see, if I could measure a reaction and get this value, however I get it, I can set that equal to this, the energy flow for this reaction, and I can put it in the back of the book. And that's exactly what we do. So the delta H of formation for barium phosphate is listed in the back of your textbook as minus 4176 kilojoules per mole. Now, what did that tell me? Is it exothermic to form this compound or endothermic? It's exothermic, very exothermic. 4,176 kilojoules. That's going to be 4.176 million joules for 1 mole of this compound. That's quite energetic, not unsurprising. Now, let's look at this reaction is involving oxidation of ammonia to make this. This is a really neat reaction. Some metals, in particular platinum, which is too expensive to worry about, and copper catalyze that reaction. They'll make it occur at a much lower temperature and at a much faster rate than it would happen in air. I mean, you know already, when you have a bottle of ammonia in the lab, it doesn't catch on fire with the oxygen in the room. It's stable. Now, this reaction would occur, and it's quite endothermic, gives off a lot of heat, but ammonia and oxygen are, that reaction just doesn't happen fast enough to ever see happening in lab because of the nature of the reaction. But if you have a catalyst, you can speed that up. So here's an experiment you can do. It has to be done in a hood, so don't do it. But you could take ammonia or acetone. There's another reaction to do the same, that's exothermic and catalyzed by copper. You can take a copper penny, one of the pennies before they made them into the crazy zinc clad pennies. But if you take a real old solid copper penny, drill a hole in it. I know that's defacing American currency, but pennies are no longer legal tender. So I think it might be even legal to drill a hole in a penny now. But anyhow, you drill a hole in it, put a wire through it, like a little piece of a guitar string or good hard steel wire through it. And you put that loop of wire on a stirring rod so that you can hang the penny from the stirring rod over a beaker containing ammonia. Then you take that penny out into a burner and heat it red hot, and then immediately put it back over the beaker of ammonia. It will sit there and glow as long as that ammonia is in the beaker. Because it catalyzes this reaction, and that reaction gives off so much heat, it keeps the penny glowing red. And it'll glow just like that until it's all of the ammonia is gone. You might do it for even hours. And it's a neat demonstration, but I said don't do it in your room because nitrogen dioxide that it forms is more toxic than the hydrogen cyanide they use in the gas chambers to kill people. So you don't want to make that in the lab, but this was a neat reaction. That's all free and extra. Now, the delta H for the reaction can calculate them from the standard enthalpies of formation. That is, I can take the energy that it takes to form 4 moles of ammonia, that's this one, and 6 moles of water gaseous, that's this one, and subtract off 4 moles of ammonia as a gas and 7 moles of oxygen. I don't have a value here. Why? It's 0. Heat of formation of oxygen, diatomic and gaseous oxygen, is the reference state. That's 0. So I can do this calculation from the table in the back of your book. I don't have to do that experiment. I could find out how much energy is going to be given to that penny by looking at this. I got 4 moles of this. The value from NO2 in the back of the book is plus 33.18 kilojoules per mole. And I've got 6 moles of water, and that's 6 times the molar heat of formation of water is minus 241.82 kilojoules per mole. Then I need to subtract off the heat of formation of 4 times the heat of formation of ammonia. In the back of the book, that's minus 46.11 kilojoules. I can do the math. And I get minus 1136.76 kilojoules of energy would be given off when 4 moles of ammonia get oxidized by this reaction. So it's quite energetic, 1.1 million joules, in other words. So that gives off a lot of energy. It's negative, telling me the heat is released, so the penny is going to get hotter and in that experiment. So that's what it looks like. Now, I want to tell you what you just calculated. Remember the standard state? Standard state is 1 atmosphere pressure and 25 degrees for every substance in the reaction. That means the partial pressure of ammonia in this standard mixture for that heat of reaction is 1 atmosphere pressure for ammonia. 1 atmosphere partial pressure for the oxygen. Everything's at 1 atmosphere pressure, right? Not 1 atmosphere lab pressure. That is the mistake almost every single book I've ever seen makes. Very few of them, if any, ever tell you. They will tell you that the standard heat of formation is for 1 atmosphere pressure. They make it sound like it's 1 atmosphere pressure in the lab. It's not. It's 1 atmosphere pressure of everything gaseous in that reaction. So the neat thing about this is that gives me a set of concentrations. What's the mole fraction of each one of them? total pressure is the sum of the partial pressures. The total pressure on this is 4 atmospheres. 1/4 of it's ammonia, 1/4 of it's oxygen, 1/4 of it's nitrogen, and 1/4 of it is water vapor. So it's 25% mole fraction of each of the gases in this particular case. Now, so the total pressure in the lab in this experiment is 4 atmospheres. Not 1 atmosphere, it's 4 atmospheres. Now, the reason why this works is we're going to make use of this later on, because when we talk about standard state, we're talking about a certain mixture of reactants and products, That's a certain fixed mixture. If there's 4 moles of gas in there, each gas is at 1/4 mole fraction. So that standard state is a standard mixture, standard concentration mixture of those things. And it's got to be, in reality, if you wanted to duplicate this, you would have to have a container so big that it would be at 4 atmosphere pressure, but you could go in there and take out 4 moles of ammonia and 7 moles of oxygen and add in 4 moles of NO2 and 6 moles of water vapor into that container, and the pressure of each gas would not change. So you've got to have so many actual moles in there that when you take out 4 moles of ammonia, the pressure of ammonia doesn't change. Its concentration doesn't change. So you've got this hypothetical mixture so big that you can do that at these pressures. Now, remember, does it really matter whether it's real or whether it's imagined? No, it doesn't. But if you take this imagined mixture, now you've got a certain set of concentrations starting out in this reaction. When this reaction is over, we're going to learn in Gen Chem 2, not all the ammonia, not all of the oxygen are totally gone. Not all, you're not going to make 4 moles of NO2. You're going to make less. You're not going to make 6 moles of ammonia. The reaction's actually not going to go to completion. But we can predict where it will go because we know where it came from. We know what the initial mixture concentrations were. And we're going to be able to calculate a point in this reaction where we've minimized the total amount of energy flow during the process. And we've not gone all the way to the end, but we reach a state where the concentrations don't change anymore. In Gen Chem 2, we'll call that equilibrium. But it's critical to understand that process. You need to understand where you came from. You need to know what these standard mixtures mean. The standard mixture for a reaction is 1 atmosphere pressure of each gas present, and if there's 4 moles, 1/4 of the moles is each kind. If there's just 3 moles of gas up there, then 1/3 of the moles of each gas would be the concentration of each one. You'd have a mole fraction of 1/3 for each one of them. So this is important. It's really, really important to understand what the standard mixture means. It's 1 atmosphere partial pressure of each of the gases present in the reaction. And the total pressure is the sum of all the partial pressures. So we want the container so large that removing 4 moles of ammonia, 7 moles of oxygen, and adding 4 more moles of nitrogen dioxide and 4 more moles of water doesn't change the partial pressure of anything involved in the reaction. That would be a huge container. And that's what it would look like. That's what our standard mixture is. The standard state fixes a specific set of concentrations for everything involved in the reaction. That's very important. Remember that. Your book didn't tell you that. Okay. Enthalpy of reaction involves a number of steps, and the sum is of the enthalpies of each step. That's Hess's law. And if you reverse the direction, you just did this in lab, you reverse the sign of the heat flow. If its reaction is exothermic one direction, it's endothermic by the same amount in the other direction. If I'm looking at this, now here's an overall reaction. I want to show you how we can use this now. I can take the 2 moles of sodium and hydroxide and 1 mole of sulfuric acid to make sodium ions. I can take the sodium ions, I'd get 2 of them, and sodium metal, 2 of them would be solid. I can add the oxygens. I've got 4 here and 2 here, 6. That would be 3 O2s. And I could take 1/8 of an S8, that would get me my sulfur. And now look, that is decomposing the reactants to products. It's the opposite of the heats of formation. Heats of formation would be taking this stuff on the right and putting it and going to these things I've got on the left. So that's the negative of the heats of formation of these two, because we switch the sign. Now I can put those same elements together and form the products. And yes, in my products, I need 2 sodiums. Well, I had 2 sodium atoms. I have enough to make 2 that. I need 1/8 of S8 to make 1 sulfur. I'm going to use 4 of the oxygens here and the other 2 here. And then the hydrogens that I need from the sulfuric acid, I need 2 waters. Now, if I add these 2 together, this one plus this one, I get this one. So in general, the heat of a reaction is the sum of the heats of formation of the products, that's this line, minus the sum of the heats of formation of the reactants, that's this line. By Hess's law, this plus this equals this. So adding these 2 heats together in this form would give me the same thing. I've got a phone call coming in. I gotta find my phone. There it is. Turn it off. I don't take calls when I'm in class. Okay, all right. So here's the heats of formation of any reaction is the sum of the heats of formation of products in the back of the book minus the sum of the heats of formation of the reactants in the back of the book. So you see, I can calculate that. There's no reason in the world I should ever need to go to the lab and measure delta H of a reaction anymore, if I know what the heats of formation of all of the components that make up the reaction. So this saves us a lot of stuff we would have to do in the lab. We don't have to do it anymore because we can calculate what it would be. And we can calculate it for 2 hypothetical reactions that can't possibly happen. There is no way I can take sodium and oxygen and sulfur and mix them together and get sodium hydroxide and sulfuric acid. It isn't going to happen. I'm going to make sodium oxide. I'm going to make sodium sulfide. I'm going to make sulfur dioxide and sulfur trioxide. In reality, I cannot do these 2 reactions. No way in the world I can ever do them. But I don't have to be able to do them. I can calculate what the energy flow would be if I could. And I can do that from tabulated data in the back of the book. Now, let's look at some different kinds of heat. I wanted to remind you that when you talk about a calorie in your cereal, it's really a kilocalorie. A food calorie is a kilocalorie. And if you take 1 gram of a substance and burn it, it's the fuel value for that something. And sometimes they'll give you the calories in a gram of your cereal or a certain serving size. That's a certain number of grams is the way they do it. And that's called the fuel value for different substances. Now, the assumption is made is that whenever you eat your Cheerios, ultimately it's going to be metabolized to carbon dioxide and water vapor. And the carbon dioxide and the water vapor you will expel. The carbon dioxide you you'll breathe in and you'll breathe out and get rid of that. And the water vapor you will perspire or eliminate it in another way that I'll not mention in polite company. But it is assumed that the metabolic energy is the same as what you get when you burn things in a bomb calorimeter. It turns out that's not quite true. The metabolic energy is usually a little less. So you can comfort yourself. You're not going to quite get the amount of energy from your Cheerios that it tells you would get on the box of Cheerios. It'll be a little less, but not a lot less. That's a good indicator anyhow of how much energy is involved. Okay. You measure fuel values in a bomb calorimeter, as I mentioned, and it's a little bit less than the fuel value. In fact, some foods, like I'm told that celery, for example, metabolically, it costs you more energy to metabolize a stick of celery than you don't get anything back. It actually uses energy. You have to use energy to metabolize it. So those are the kind of foods that would be good in your diet, is the ones that actually have a positive metabolic energy level. Okay, here's some uses of Hess's law, and we're given two reactions. I can take SO2 and react it with oxygen. It will burn with a catalyst to make SO3. If I do, I get minus 196 kilojoules. I can take sulfur and burn it in oxygen to make SO3. If I do, I get out 790 kilojoules. What if I wanted to calculate the heat of the reaction to go to SO2? Well, I can use Hess's law. Now, the way you do that is you look at this equation. This is their target equation. And I'm going to look at that, and I'm going to pick the most complex thing in the target equation I can get. Well, I think SO2 is the more complex one in that one. So I'm going to focus my attention on SO2. Now I'm going to look up here and find a reaction that's got SO2 in it. That would be number one. Okay, so now this is the SO2, and its heat flow from reaction 1 is minus 196, but I want the SO2 on the product side. So I'm going to turn it around. And if I turn it around, the heat flow would now be plus 196. It was exothermic one direction, it's endothermic the other. Now, but that's still bad. I want one of these instead of two of them. So I need to divide this equation through by 2. So I divide that through by 2, and well, I don't guess I have to for this one. No, because I'm going to cancel that out right here. So now look at my, I get the same coefficient. Yes, I did do that. Divide by 2, I get that. Okay. Now this is my new working equation. It's got the SO2 in the same place with the same coefficient that it has in my target equation. Now this becomes my working equation. From here on, I want to get rid of things that's in here that's not in my target. And again, I'm going to pick the most complex one. This one's not in my, well, it is in my target, but this is more complex. So what I'm going to do is try to get rid of the SO3 using the other equation. All right, so here we go. So I need SO3 on this side, and I need 2 of them. So when I do it like this, I get this equation by getting this turned around in the direction I want with the coefficient that I want. I wanted a coefficient of 1, so it would cancel the coefficient of 1 in this working equation. I'm going to combine these together. When I do that, I get my new working equation. So when I combine all of this and reduce to the smallest sets of coefficients, I get sulfur plus 1 oxygen. It goes to SO2. Now this is my new working equation. And that's the heat it would have by just adding these together. I get this heat value. Now, that's my new working equation. What I do now is compare the working equation with the target, and I want to eliminate anything that's still in my working equation that's not in the target. Well, here they're the same. So you keep doing that until the working equation you have equals the target equation you want. And then you're done. Okay, so that is a Hess's law problem given these two reactants. Here's the checkpoint on this, so I need to work that with you. Okay. Okay, so I need to stop the share. Now, oh, wait. No, you know what? I don't need to stop share here. That's not the one that's going to actually be the, I need to go back to share screen. And I need to go back to, okay. Now, here's a set of 3 given equations. I've got C2H6. I can burn in air easily. I can carry out that reaction very easily. When I do, I measure a heat flow of minus 3119.4 kilojoules. That's a compound called ethane. Here's another compound called ethylene, and I can burn that. And I would get minus 1410.9 kilojoules. I can take hydrogen and burn it with oxygen to make water liquid, and I get this value. Now, I'm trying to get the energy of this reaction up here. What energy would be involved if ethane went to ethylene and hydrogen? That might be an interesting reaction for us to know about. But I can take these 2 combustion equations, and so what am I going to do? I'm going to look at this and I'm going to say, okay, here's my target. What's the most complex looking thing in the target equation? It's the C2H6, I think. So what I'm going to do is I want to use this reaction, but I want a 1 for that coefficient. So I'm going to take this given equation, divide it through by 2, that will give me this equation. If I divide the heat flow by 2, that gives me this equation. This becomes my first working equation. Now, I want to get rid of something that's in this that's not in the target. Well, there's no carbon dioxide in the target. So, all right, I want to eliminate the carbon dioxide then. And I want to use the second equation, this one, to get rid of the carbon dioxide that I have in this equation. This one's got 2 carbon dioxides. The second equation also has 2 carbon dioxides, but they're on the product side. So I add these together to produce my second working equation. So now what I've done is I've added these 2 together, the 2 CO2s from the second equation. It's been reversed. That's why the sign was positive. And then the 2 CO2s from this one cancels the 2 CO2s from this one. Add together, you get this one. Add the 2 heats together, you get this one. So this is the heat. Now that's 7/2 of an O2, not 7/20 with a subscript 2. That maybe needs a space right there. So now this is another working equation. You always go and look at the working equation and the target. In the working equation, the C2H6 is in the right place with the right coefficient. In this new working equation, the C2H4 is in the right place, product, with the right coefficients. So I just need to get rid of some of these things in this one to go to my next working equation. Now, if I divide that through by 2, then and reverse the second equation, I eliminated the CO2. I got that. Oh, come on. Now, if I now take this, I'm getting rid of the water. And in my working equation, I want to get rid of the water that I had in it. And I've still got 1 water in there. And I can do that by adding the half of this second equation. So, and turning it around. So I want to turn that around. That'll change the sign to positive. Divided by 2, that makes it 285. Now when I add them 2 together, the waters cancel and the half O2s cancel, and I'm left with this as my new working equation. But since this now is the same as the target, then the heat flow for the target equation is what I got by Hess's law for the heat flow for the reaction, plus 137. Now this would be the one that you should work. And I think what I want to do is I will work this with you when we pick up lecture again, but if you want me to. But what I would really like for you to do is try one of these for yourself. So let's think about how we're going to do it. Here is up here at the top, right here, is my target equation. If I ask you what's the most complex thing in that reaction, what would you say? This one, right? Do you see one of the 3 equations that has that in it? Okay. Is it on the correct side with the correct coefficient? Then what do? Okay. Now, you'll have a new working equation, and you'll have the strontium carbonate on the product side. Now, what do? Well, I want to take out anything that's in this that's not in the reaction up here. Well, I would have SR. I've got strontium oxide and carbon dioxide. I'd probably eliminate the strontium oxide. So I'm going to get my target equation. I'm going to now try to eliminate the strontium oxide. Do you see one of the 3 equations that's got that in it? Hint, hint, hint. Okay, you see the point? Follow that through and practice it to see that you can do it. And then if you can't do it, I will work it with you. But I think it really is good to try to do that on your own. And here's the heat of reaction of the ammonia oxidation, but now we're going to a different product. Instead of NO2, we're going to NO and this. And so it's the heat of formation of products. Okay, I've got 6 waters as gaseous. So 6 times the delta H of formation of gaseous water, plus 4 times the delta H of formation of NO, not NO2 this time, NO, minus 3 times the delta H of formation of ammonia. You don't need the 5 oxygens because oxygen is diatomic and gaseous at room temperature, and so its standard value is 0. That's my reference value. Plug in my numbers, solve for the reaction. And then here again, one that you could do. And again, I've worked some like this already. Let's save this one. And again, you try it, see if it makes sense to you, see if you can get a reasonable answer. And if you're not confident in it, just email me or and I'll work through it with you. Okay, now, let's see. I didn't need to go there. Gee whiz. let's back up. I'm about at a place where I think I should stop. Okay, let's go ahead and I'll stop with this. I'll pick up here tomorrow. We've got easily enough time tomorrow to finish everything. And remember now, tomorrow we've got one more full lecture. Then Wednesday we have our exam on exam 4 to finish out the course. So we'll pick up on that with then tomorrow. Okay, let's take maybe a little bit longer break right now. Let's go to pick up about 12:15, 11:15. Oh, yeah, 11 o'clock, 11:15. Let's pick up at 11:15. And we'll be talking about the last lab, and that will be the under pressure lab, but it's not the one, it's exactly the same as the lab manual. It's the one that we have on D2L. And I'll discuss that with you in about beginning about 11:15. Okay, let's stop the share. And so I say maybe it'll get done by the time I get back. Okay.